After LC serial resonance and LC parallel resonance, let's discuss general case. The one-port network only contains inductors and capacitors, so the port impedance only has an imaginary part. It's often expressed as the form that the numerator and the denominator are both functions of angular frequency. According to the previous discussion, we can find that F1 omega equals 0 means the circuit has serial resonance. And F2 equals 0 means the circuit has a parallel resonance. This helps us solve complicated LC resonant circuit more easily. Next, let's take an example in which an inductor is connected in parallel with a capacitor and then in serial with a capacitor. We draw the frequency characteristic of the port reactance firstly and then solve its resonant frequency. You know that the circuit is short seen from the port in serial resonance and open seen from the port in parallel resonance. Let's focus on this part of the circuit firstly. When L1 and C2 have parallel resonance, it's an open circuit seen from here. So it's open circuit seen from here too. The whole circuit has parallel resonance. The reactance characteristic of L1C2 parallel resonant circuit is like this. The parallel resonant angular frequency is omega 2. You can find when omega is larger than omega 2, the circuit represents the characteristic of a capacitor seen from the port to the right. This capacitor connects this capacitor in series, so the whole circuit represents the characteristic of the capacitor. When omega is less than omega 2, the circuit represents the characteristic of the inductor seen from this port to right, but it's not a pure inductor because the pure inductor increases with the frequency linearly. But it decays from the positive infinite to 0, so it covers all the inductance values in a nonlinear way. At some frequency, this inductor and the capacitor will have serial resonance. The reactance characteristic of the whole circuit is like this. The intersection is omega 1. When omega is larger than omega 2, the reactance seen from the port is a parallel connection of C2 and this equivalent capacitor. So the red curve may change a little, but anyway, it's a capacitor. So qualitatively, the frequency characteristic is still like this. The blue curve is the frequency characteristic of the port reactance. The circuit has a smaller serial resonant frequency and a larger parallel resonant frequency. Now let's verify this conclusion by quantitative analysis. It's an expression of the reactance seen from the port. It can be transformed into this form. When the numerator is 0, we can solve omega 1. When the denominator is 0, we can solve omega 2. The result of a quantitative analysis fits the qualitative drawing of the frequency characteristic of the port reactance. We need to point out that you should be familiar with the frequency characteristic of the port reactance in LC serial resonance and parallel resonance, which is very helpful for the qualitative analysis. Now, we have a question for you. Here, the excitation of the circuit has two frequencies, and omega 1 is less than omega 2. Now we need to design a signal processing circuit or a filter. We want that after the filter, the load only has omega 1 and the signal with omega 2 has been eliminated. How to design this filter? By the knowledge of LC resonance? Please think about it.